Let's go ahead and get started. So we had a quiz the other day. It was supposed to be due Monday, but because I didn't put a due date on it, I made it due yesterday, and most of you guys did okay on it. But let's go ahead and address that real fast. So I want to go back to the quiz, and let's take a look at it. So this quiz dealt with the right-hand rule, and we had to remember how to work those things out. So in the case of this first one, you're standing in front of a door, and you're going to have to visualize this. The hinges are on the left side of the door, and you're pushing it away. So the door is rotating away from you, and I want to know what torque vector you've created in order to open that door up. And in order to understand the direction of a torque vector, you know that the door is rotating away from you. And the way you can find the direction of the torque vector is you take your right hand, and if you just curl your fingers in the direction that the thing is spinning, your thumb is going to be pointing in the direction of the torque vector. So you can see that in this example, the torque vector is going to be pointing straight up. Now you could also do the full-on right-hand rule with this. The way you would do that is you're opening the door, which means you're reaching over on the doorknob and pushing the doorknob forward, away from you. And so that's the direction of F, away from you. Now, R, the moment arm, points from the hinges, which are over on your left, toward where you're applying the force. So the R vector points to your right. So what you would do for the right-hand rule is you would do R cross F. So you take your right hand, you would stick your fingers in the direction of the moment arm vector, R, which is to the right. But then, with your fingers pointing to the right, you want to bend your fingers in the direction of the force, which is, in this case, toward the camera or away from me. So I have to rotate my hand and bend them toward the camera. My thumb is pointing upwards. So the full-on right-hand rule will help you do that as well. So question 2. I've got a child sitting on the left-hand side of a seesaw, and I want to find the direction of the torque vector created by that child. So here's a seesaw, and what's going to happen is the child sits on the left-hand side of the seesaw. This is my left, and pulls downward. So what's going to happen is the seesaw is going to rotate, from my perspective, counterclockwise. So the torque vector is going to point towards me. So the answer is toward the observer. Question 3 is straight up right-hand rule stuff. I've got a vector pointing to the left. The second vector points down, and I want to do A cross B. So I put my fingers in the direction of vector A, which is to my left. Then vector B points down. The torque vector points toward the observer. Now, the last question is a little bit tricky. And in order for you to get that, you have to remember something. And that is, how do you actually evaluate one of these torque vectors? Let me switch the screen share over to the camera so I can draw. Because what's going to happen here is, since torque is R cross F, when you're actually evaluating the magnitude of the torque, you want to find out how big the torque is. The way you would deal with the direction part is you'd say that the magnitude of the torque, just the number part, is going to be the magnitude of R times the magnitude of F times the sine of the angle between R and F. And the reason that matters is because in this example I have A cross B. So A cross B, same kind of reasoning, would be the magnitude of A times the magnitude of B times the sine of the angle between A and B. But in this problem, A is up and B is down. So the angle between them is 180 degrees. And since the sine of 180 is 0, it means that it doesn't matter how big A or B is. I'm going to multiply them by 0, so my answer is going to end up being 0. So in this case, there would be absolutely no cross product, and the answer is 0. So a lot of you guys got the first 3, and then you swung and missed on the fourth one, because the fourth one was a little bit tricky, and you had to introduce another concept that made it a little bit less obvious. Okay, any questions about that?
You said the last one was no torque?
Yep, there's no torque. The answer was 0. All right, so here's where we're going today. Just a reminder, the exam is on Monday. It's going to cover chapter 7, 8, and 9. But what we're going to do today and, well, at least today, is we're going to introduce some additional rotational stuff where, unlike chapter 9, we're going to allow things to actually rotate. But in order for us to do that, we're going to have to generate a new set of nomenclature. We're going to have to be able to describe how something is rotating in the same fashion that back in chapter 2, we had to be able to describe how an object was moving translationally. And it turns out that what's going to happen in chapter 10 is there's going to be a ton of material in chapter 10. And it might seem overwhelming until you stop and realize that what's really happening in chapter 10 is that literally everything we've done up until this point for translational motion, remember translational means going up, down, left, right, forward, backwards. Everything we've done for translational motion is going to end up having an analogy in rotational motion. And so all we're really doing is learning how to reframe the stuff we did back in chapters 2 and 3 and use it in the context of an object that is rotating. So what will happen is there'll be a rotational equivalent for all the stuff from chapter 2. There'll be a rotational equivalent for F equals ma that we learned in chapters 4 through 6. There'll be a rotational equivalent to kinetic energy that we learned in chapter 7. There'll be a rotational equivalent to momentum that we learned in chapter 8. So all we're really doing in this chapter is learning what those equivalents are and how to apply them to a thing that is rotating. So today, what we're going to focus on is rotational kinematics. And how do I describe the motion of an object that is rotating rather than translating? And the best way I found to do this is to just sort of track this alongside the stuff we did back in chapter 2. So you can sort of see the one-to-one equivalencies as you start to learn this new stuff. So that's what we're going to do. So let's think back to the very first stuff we ever learned in this class, kinematics. And what I'm going to do is I'm going to take, let's use the blue pen, it writes a little better. I'm just going to divide this sheet in half. And everything on the left-hand side is going to be translation. Everything on the right-hand side is going to be rotation. So this is the stuff where the new stuff's going to go, and this is just the old stuff that the new stuff is related to. So back in chapter 2, we learned how to describe the motion of an object, and there were several kinematic variables that we had to become familiar with. Right? The first thing that we had to learn how to describe in chapter 2 was the position of an object. So in translational motion, we had position. Now, what was the symbol that we used to represent position? What variable represented a position back in chapter 2?
X.
Yeah. Position was always X, or even in chapter 3, it could be X or Y, right? But let's stick with X. What units do we measure position in?
Is it I had J hats?
I-hats and J-hats gave us a way of tagging the direction for the position, or any vector for that matter. But what I'm looking for is, like, if you're measuring a position, what units would it be in?
Meters.
Yeah, it would always be some kind of unit of length, like meters. And the way it worked was, if you recall, we always chose a frame of reference, right? Some coordinate system, and we'd measure how far the object was from that frame of reference. So, like, the very, very, very first example we ever did is I drew that stupid tree and a bunch of stick figures, right? And I would use the tree as my frame of reference. I would call the tree x equals 0, and then I just measure where something was relative to that tree. So that's how we're going to measure position back in translational motion. Now, for rotation, what's going to happen is things are going to get a little bit tricky. And to see why that is, I'm going to bring that back into a second. But if, let's say I've got a big long stick, and I'm going to have that big long stick rotate around an axis here at the end. And what's going to happen is this thing's going to rotate like so. And so later on, maybe my stick is oriented slightly differently. So if I were to ask you about the position of the stick, it's not as easy with rotation. Back in chapter 2, we often talked about changes in position, and of course that had a name. It was called displacement. Displacement is just the change in position, or delta x. What's going to happen is, if I'm talking about this situation, oh, I smeared it. Good job. If I'm talking about this situation, well, displacement would be how far an object has moved. But if I'm talking about how far this stick has moved, I run into an issue. Because right here at this end of the stick, that end of the stick hasn't gone anywhere. It started here and it ends up here. So the displacement of the stick at this end is 0. But if I'm looking at this little portion of the stick, it has traveled through a circular arc, and it's moved that far. This end of the stick has moved much further, right? So if I'm talking about the position of the stick or the displacement of the stick, it's going to matter what portion of the stick I'm referring to. Different pieces of the stick will be at different positions and will have taken different amounts of displacement depending on where they are. Does that make sense? So we can't just use the language of displacement for talking about where something is. So what we're going to do instead is we're just going to track it differently. Because what's going to happen is, rather than track how many meters this section of the stick has passed through, I am instead going to track what angle it has passed through. Because what's going to happen is, if this is a 30-degree angle, how far has this guy moved? 30 degrees. How far has this guy moved? 30 degrees. So the angle that has been passed through by every section of this stick is always the same. So the way we'll keep track of positions in rotational motion is by using an angle as the thing that we measure. Rather than a distance in meters, we'll measure an angle in either radians or degrees. And so this is going to give us the rotational equivalent to position, and that is what we call angular position. Come on. So angular position, we're going to measure with the angle theta. It'll have units of, typically radians will be preferable, but sometimes we could use degrees or even revolutions. If you have a wheel that is spinning and I ask you, how far has this wheel spun? I could say it has gone through 2 revolutions. It spun all the way around twice. Does that make sense? So the way we'll measure that is, if this is my stick, what we will do is, here's my axis. We'll just choose some reference location to be theta equals 0. Just like back in chapter 2, we always had to choose where x equals 0. I might say, aha, when the stick is oriented like this, I'm going to refer to this orientation where I'm going to measure the angle from this reference point, and I'm going to call this theta is equal to 0. Then what's going to happen is, later on, it will have rotated through some angle, and so maybe this is 30 degrees, so this orientation of the stick would be theta equals 30 degrees, or in radians, that's pi over 6 radians. Later on, if I've rotated it until it's straight up vertical, then that would be obviously theta equals 90, or pi over 2 radians. Right? And you can just keep track of how far it has rotated, always referring to that initial orientation. So if you make one complete revolution, that would be 2 pi radians, or 360 degrees. If you went all the way around past that point, imagine I spun all the way around once, and then up to here, well, that's going to be 360 degrees plus another 30, so 390 degrees, which is 7 pi over 6 radians. And you can track things that way. Right? But all we're doing is just paying attention to how far it's rotated past some initial reference point. And 9 times out of 10, we're going to pick that initial reference point to be 0. So, super easy. We can do that in our sleep. Now, back in chapter 2, we started with position and displacement, but very quickly we began talking about velocity. What's the definition of velocity? Nobody knows.
What was your question?
What's the definition of velocity?
Oh, wait, the definition?
Yeah. Because what we're doing is we're reestablishing definitions of all these things. So we need to know the definition of these things that we're equivalent to.
It's distance over time, right?
Close. It's the change in position over time.
Right.
Dr. Fun, I have a question. What does that say under degrees?
Revolutions.
Okay.
Sometimes you'll measure angular positions not in terms of radians or degrees, but in terms of how many times it's rotated around. We'll talk about that in a minute. So velocity was the change in position over time. And of course, you would measure that in meters per second. What's going to happen is when you have a rotating object, we're going to run into the same problem. Because imagine I'm spinning my pen around an axis in the middle. Well, if I'm looking at the very, very outside of the pen, and the pen spins all the way around once, and it takes, let's say, 2 seconds, then what's going to happen is the outside of the pen traveled a distance of 1 circumference, 2 pi r, all the way around. But the middle of the pen traveled around a much smaller circle. It went a smaller distance. So the further out you are on the pen, the bigger speed you have to have, because you've got to go around a larger distance in the same amount of time that the middle of the pen goes around. Because it takes 2 seconds for any part of the pen to go around, but they're all traveling around circles of different sizes. So talking about velocity for a rotating object sucks, because different pieces of the rotating object are going to have different velocities. So rather than do that, we're going to define something called angular velocity. And angular velocity is going to be, instead of being the change in position over time, it's going to be the change in angular position over time. And we're going to use the symbol omega. I see your hand, Amber. Hold up 1 second. So angular velocity will be the change in angular position over time. And that'll be measured in, say, radians per second, or degrees per second, or revolutions per second. All right, what's your question?
Does displacement not have a rotation side?
Oh, you could have had an angular displacement. I just didn't write it. And of course, that would just be delta theta. All right, so far so good?
Wait, I have
So-
a question.
Yes.
Remember when you wrote the angle that was like vertical? No, horizontal, and then you wrote the vertical, and then you wrote the one in the middle. Is that angular displacement or angular position?
Well, either way. So for instance, if I'm calling horizontal angle 0, right? And later on my object is straight up and down, well, it's not at angle 0, it's at angle 90 or pi over 2. So if I'm talking about like what orientation the object is currently in, that's going to be what angle it has been rotated from based on that reference angle. So I'm always calling this angle 0, so the angle that this makes, or the angle between 0 and here, is the angular position. The angular displacement would just be how far it has moved, which in this case, if I'm going from 0, the angular displacement and the angular position would be the same. The way the angular displacement and the angular position might be different is, imagine I had an object that started off at pi over 4, or 45 degrees. It moves to pi over 2, or 90 degrees. So it rotates from here to here. So when it's like this, the angular position is 90 degrees, or pi over 2. But the angular displacement that it had was from here to here. Instead of being 90 degrees, it'd be just the 45 degrees that it moved to get from here to here. Does that make sense?
Yes.
Okay. So that's the distinction, and it's one you should be. It's mostly one of usage rather than of anything more theoretical, I guess. So anyway, angular velocity. This is the Greek letter omega. It looks like a little lowercase scripty w, but it's not a w. And if you call it w, I die a little inside. It is lowercase omega, and omega is the change in angular position over time. Super easy. Now, after we did velocity back in chapter 2, where did we go next? What was the last kinematic variable that we had to track back in chapter 2? Already bored. Acceleration. Right. Now, what was the definition of acceleration? Do. What is acceleration?
Distance and time.
Nope.
What?
Isn't it the rate of change?
It is a rate of change, but it's the rate of change of what, Brittany?
Didn't get that far. I just
That's a start. Well, so if you recall, velocity was also a rate of change. It was the rate of change of position. Acceleration is the rate of change of something else.
Speed.
Is what?
Is it the slope?
It turns out to be a slope. The slope is a way of establishing the rate of change. But the way we defined it was that it was the rate of change of velocity. So if your velocity is changing, if you have one velocity at one moment and a different velocity a little bit later, you are accelerating, right? Velocity was a rate of change of your position. If you're in one location at one moment and a moment later you're someplace else, your position has changed. Velocity is a measure of how quickly that change occurred. Acceleration is about how your velocity is changing from moment to moment. If you have a large acceleration, it means that your velocity a moment from now is going to be wildly different from what it is now. You'll have a huge change over a short amount of time. And if your acceleration is small, it means that your velocity a moment from now is going to be not very much different from your velocity right now. And if your acceleration were 0, it means that whatever velocity you have now, it's the same a moment later. Your velocity is not changing. So that's the basic idea. Now, we're going to introduce the angular equivalent, angular acceleration. And for that, we're going to use the Greek letter alpha. It looks like a little fish, but it's not a fish. It is alpha. And when you call it a fish, I die inside. And we're going to define alpha the same way. If this is the change in velocity over time, this is going to be the change in angular velocity over time. So if your angular velocity is changing, you have an angular acceleration. So if your object is spinning, but the rate it spins with is starting to speed up or slow down, it has an angular acceleration. What are the units of that going to be? Well, regular acceleration was meters per second, or meters per second squared. This will be the same kind of deal. Omega was radians per second, so it's going to be radians per second, or radians per second squared. So what's going to happen is each of these variables we had back in chapter 2 has an angular version that we'll use when we do rotation problems. Now, the cool part about all of this is that once we've established the existence of these analogies, you'll notice that the mathematical way they're related to each other are all very similar, right? The relationship between velocity and acceleration is the same whether I'm talking about angular velocity or translational velocity. This is delta x over delta t, this is delta theta over delta t. Because these definitions mirror each other so well, several other relationships between these variables are also going to mirror one another just as easily. So think back to chapter 2. We had those 4 equations of motion. And what's going to happen is each of those 4 equations of motion is still going to work today. All we've got to do is replace the linear variable that we used back in chapter 2 with its angular equivalent. So we had in chapter 2 what I call the position equation, which you probably have all learned to know and love. Right? We used that back in chapter 2. But if I have a rotating object, I can replace this equation with what I might call the angular position equation. And all I'm going to have to do is swap out whatever variable I have here with the translational version of that same variable. So for instance, I will replace all of the x's with thetas. I'll replace all the v's with omegas. I'll replace all the a's with alphas. So my translational position equation turns into my angular position equation by replacing this with theta final, this with theta initial, this with omega initial. Now, time is not a vector, and so t is just t, plus 1/2, not a, but alpha, t squared. So all I had to do was invent this new equation based on what I knew from chapter 2. You do the same thing with the velocity equation, right? Velocity was v initial plus at. That was the chapter 2 version. The chapter 10 version is going to be replacing v with omega v initial with omega initial, and a with alpha, right? If I take the stopping distance equation, it's going to work too. So that was v final squared equals v initial squared plus 2a x final minus x initial. Again, I can replace that. Omega final squared equals omega initial squared plus 2 alpha theta final minus theta initial. And of course, the last one we had in chapter 4 was the useless equation, x final equals x initial plus 1/2 v final plus v initial times t. I found that to be the least useful of the 4. But that's going to turn into so each of those 4 translational equations has a rotational equivalent, and you can solve kinematic problems in rotational coordinates just as easily as you could back in chapter 2 doing it in translational coordinates. It's literally the same process. So far, so good?
I have a
So,
question.
yeah,
What chapter is this?
this is chapter 10. Yeah, chapter 9 introduces the concept of torque, which makes things want to rotate. But chapter 10 is where we're going to start actually letting things start to spin. And so we have to learn how to describe how to make it spin. And this is how we're going to do it. So
I have
let's
another question.
Yes, ma'am.
Are we gonna still have a review day or something on Friday?
We're going to spend a little time on Friday.
Okay.
Yeah. All right. So far, so good. You guys with me? All right. So what's going to happen now is let's do a rotational kinematics problem. Let's just flip this over. So let's talk about, well, let's say that I've got a playground merry-go-round. And what's going to happen is little kid's going to get on the playground merry-go-round, and the merry-go-round is going to start at rest. However, after 10 seconds, the boy has gone around twice. So far, so good. So what I'd like to know is that if the acceleration of this thing is constant, I'd like to determine A, the angular acceleration, and B, I'd like to figure out what is the final angular velocity. So I'm writing this out in words because half of the problem here is picking out what you've been told from the information that you've been given. So we're going to approach this problem the same way we approached problems way back in chapter 2. Right? It's kinematics because I'm just describing how he moves, and I don't especially care about why. What's really happening is there's probably some other kid, pushing on the edge of this merry-go-round to pick up speed, and that person is, exerting a torque. The torque is making it rotate, but we'll deal with all of that in a later chapter. Right now, we don't care why the merry-go-round is spinning up. We just know that it's spinning up. And since it's just a kinematics question, we're going to have 6 things we have to track. Just like back in chapter 2, we're going to have to know the initial position, the final position, the initial velocity, final velocity, acceleration, and time. Those are the 6 things that I'm going to have to track. So of those 6 things, which of those 6 things do I know?
The starting.
The starting what?
Position is at rest.
Yes, I read.
Well, position, remember, at rest is not about position. That's about velocity.
It's the velocity.
So the initial velocity is 0. So, omega initial is given in the problem to be 0. So that's one of my 6 things that I know.
Time is 10 seconds.
I know that it took 10 seconds. Perfect. All right, what else do I know? I'm going to need more than that. Okay,
I
so
have a question. If it says that the boy went around twice, would you double the time?
no, it says it took 10 seconds to go around twice. So obviously it took some amount of time for him to go around the first time and another amount of time to go around the second time. And those 2 times better add up to 10.
Okay.
Now, notice it doesn't have to be 5 and 5 because he probably started out going slow. So the first trip around probably took longer than the second trip around.
Okay.
He's speeding up the whole time. So the big question is, obviously, we don't know alpha or omega because the question is asking me about both of those things. So both of these are unknown, which means I probably know something about the positions, and I just haven't put it into words yet. So back in chapter 2, when we were dealing with positions, you had to choose a coordinate system. You had to pick some location and call that x equals 0, and then measure everything else from that. In chapter 10, the same thing is true. So what I'm going to do is I'm going to say, wherever the boy is originally, I'm going to call that theta equals 0. Right? So when he's here, he's at an angle of 0. And he starts here, so his initial position is going to be 0. I'm choosing to call the location he starts at 0. But then what's going to happen is, over the course of 10 seconds, his angular position is going to change. He's going to go all the way around and all the way around again. So what's his final angular position?
Is it 0?
No, because it's kind of like, what's tricky here is that if you start someplace and you go all the way around back to where you started at, in terms of your angular position is not the same. Because what happened was you've gone all the way around. My angular position has to take into account the fact that I went all the way around. So I wouldn't say, oh, here's 0, here's 90, here's 180, here's 270, and now I'm back to 0 again. I would instead say that here's 0, here's 90, here's 180, here's 270, here's 360. But then I'm going to keep going, right? So from 360, I'm going to go another 90, 450, blah, 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 losing track, 720. Does that make sense?
Yes.
So what's going to happen is he's going to go all the way around twice. So theta final is going to be 2 trips around the circle, which is 360 degrees times 2, 720 degrees. But I don't want to do that in degrees because degrees are not the best units for this. I'll do it in radians. So how many radians is that?
Is it 2 pi?
2 pi is once around the circle. So it's double that. It's 4 pi.
4 pi.
We'll talk about why I keep using radians instead of degrees here in a minute. But it turns out there's a reason that I'm going to prefer to use radians than to use degrees. There's going to be some places where using degrees or revolutions or whatnot will mess you up. So, at this point, I've got, of my 6 things, I know all but 2 of them. And we've got plenty of experience doing this kind of stuff before. The trick is, if I want to figure out alpha, then I need to have an equation of motion that includes alpha without including omega final. So of those, which of my 4 equations of motion is going to have the acceleration in it, but not have the final velocity?
The one that has your angular velocity squared, that one?
You're thinking of the stopping distance equation, which is omega final squared plus omega initial squared. So it's just have them written down somewhere. Yeah, so this one here has the final angular velocity.
Oh wait, yeah, never mind.
But it also has alpha in it. So this one is a bust. I need one that doesn't have the final velocity. And
is it a position one then?
Yeah, because this one has alpha in it. I can solve for alpha, but nowhere in this do I ever have the final angular velocity. So what I can do is use the angular position formula. So theta final is going to equal theta initial plus omega initial t plus 1/2 alpha t squared. And of course, in this particular example, theta initial was already 0. Haha. Omega initial also already 0. That's going to kill this whole term. So all I've got to do is take theta final is 1/2 alpha t squared, and I'm solving it for alpha. So I'll multiply by 2. So 2 theta over t squared, and I have alpha, which in this case, it's going to be 2 times 4 pi, so 8 pi divided by 10 squared. So 8 times pi divided by 100. I get 0.2512. Radians per second squared. Piece of cake. So now that I've done that and I want to figure out the final angular velocity, at this point I know literally everything in my inventory. So any equation would do, right? Except I want to be lazy. The simplest one would just be the velocity equation. So omega final would equal omega initial plus alpha times t. Oh yeah, this is 0. So alpha times t, well, that was easy, 2.512 radians per second. So all those skills you guys developed back in Chapter 2 are going to come back and be super, super helpful in Chapter 10, because everything we learned in Chapter 2 has a rotational equivalent. And we can do rotational kinematics super, super easily. Well, one thing I should probably address, because sometimes students aren't super, they're not super confident about their ability to use radians and think in radians. And there's a reason why you probably want to be. And the reason is this. It turns out that all of your angular variables and all of your linear variables are related. So for instance, if I'm looking at this example here where I have a stick, and I move through some delta theta, some angular displacement, every part of that stick has the same angular displacement. It's going to be whatever this angle is for every part of the stick. However, the distance traveled by each part of the stick will not be the same. So the outside part of the stick would travel a larger distance. The inside part of the stick would travel a smaller distance. Now, this curved distance in math is called the arc length. And we'd use the letter S to represent the arc length. So arc length would be measured in meters. It's how many meters that section has traveled. And what's going to happen is the arc length is related to the angular displacement, because all I've got to do is multiply by r, where r is that. And this might seem like it's something new, but it's totally not. You already knew this. You've known this for years. Because what if delta theta was going all the way around the circle? If I go all the way around the circle, one complete revolution, how far have I gone? Well, that's one circumference, right? That's one circumference around a circle. What's the circumference around a circle? That's when delta theta would equal 2 pi. So the arc length, if you go all the way around a circle, is 2 pi r, which is the formula for circumference. If I only went halfway around the circle, then I wouldn't be going 2 pi radians around. I'd be going pi radians around. So pi times r would be the arc length of half a circle. So to get the arc length of any portion of a circle, I just multiply by the angular displacement of that portion of the circle times the radius of the circle. And this is why we like to use radians, because technically radians are dimensionless. And that makes the units on something like this work out properly, because S is going to be measured in meters. And over here, this has got no units at all, because radians aren't technically a unit, times R, which has units of meters. So I got meters on the right-hand side, I've got meters on the left-hand side. This is a dimensionally correct expression. And the cool part is that what will happen is all of my angular variables will be related to my linear variables in a very similar way. It turns out that if I want to know the linear velocity being traveled by, let's say, a bug on the end of this stick, that's going to equal the angular velocity of the stick times r. If I want to know the angular acceleration, or the linear acceleration, that's going to equal alpha times r. So what's going to happen is I can go from angular variables to linear variables super, super easily, provided that my angular variables are in terms of radians. These equations will break if you plug degrees in, right? Don't ever use degrees in these relationships, because the units will be messed up, because degrees, unlike radians, are not dimensionless. And so it's going to be super important you guys be able to work well with degrees or radians and convert back and forth between the two of them. Hopefully you guys learned that in your math classes, but a lot of you have slept since then and maybe have not remembered everything you want to remember. So remember that 360 degrees is the same as 2 pi radians. And so if I say I've got 53 degrees and I want to convert that into radians, the way I would do that is I'm going to multiply, and since I want degrees to cancel, I'll put 360 on the bottom. I'll multiply by 2 pi radians, and so the degrees will cancel. So to convert 53 degrees into radians, I'd multiply by 2 pi and then divide by 360.
So I have a question about the lab.
Uh-huh.
I know initially you had said that you were going to switch it up a little bit.
Yeah, we'll talk about that tomorrow.
Okay.
But yeah,
Wait, so the lab is not due like at 11:59?
it will. We'll talk about it tomorrow. I'm not sure exactly how that's going to play out. There will be something due tomorrow, but it will not be the entire lab report. Does that make sense?
Yeah.
Yeah. But let me defer that until I've made sure I know myself what I want to do. I don't want to have to say something now and then backtrack on it tomorrow. So, when you want to convert from radians to degrees, that's the way you'll do it. If you wanted to convert from radians back to degrees, you would just reverse this ratio. So other than that, I think we've got a pretty good handle on rotational kinematics. We'll look at rotational dynamics when we get back to it, and I will see you guys tomorrow.